Here comes more proper approximation. Uh, we know for this given state model, the solution to the state model x of t is given as this formula. Okay, have this homogeneous part and non-homogeneous part here. So we directly use this the formula for the discretization of this continuous model. Okay, so idea is following. So here the t is now replaced with k plus 1. This is k plus 1 times t. Okay, it's the same thing. Again, I'm not saying the t is equal to 1 second. It can be any sample time, but for the sake of notational simplicity, now this t is dropped. But k plus 1 is basically kt plus t. Okay, so you plug in this this expression for the t here, then eventually so you are going to have this. So this one times that will give you this. So this is now k plus 1 t. Okay, you split this kt plus 1 t into kt plus t. So you have kt and t. And then now this one is kt plus t, right? And so you have kt here and t. So if you multiply this guy and this one, then you have this. Okay, and also the integral. So this is kt plus t, right? So the integral from 0 to kt plus t is also split into two parts. So 0 to kt and kt to kt plus t. Okay, so it's the same expression here. This integrand here is same, but actually this one times this one is same as this one. Okay, so it's basically the same as this one with k plus 1 times t in place of small t. Okay, and then what happens here is to apply this zero the hold for this u. Okay, so during this time interval of kt plus t, we assume that this u, the control input, is constant. So if this is constant, right, then this one here is just simply copy this part here and this one here, and then now this is assumed to be ukt. Okay, so you have the u during this time interval, okay, from kt to kt plus t, but you assume that this is constant to be u of kt. Okay, then you can take this guy outside because this is not being integrated. Okay, this is constant value. You take this outside and here. Okay, and also you see that this part here, this part, this is in fact x of kt. Okay, you plug in kt here, kt, 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 you exactly got this expression. Okay, so now EAT, and this is x of kt comes, and this one here, with the assumption of this constant u, we have this part times this. Okay, but now using this change of variable, if you just change this guy to alpha, then you can see this integration is same as this. Okay, this becomes alpha and d tau becomes minus d alpha, and the kt here, if you plug in kt here, then it's t, and if you plug in this one here, then it becomes 0. But it's the same as that. If you just use this negative sign to swap this interval, then you have this. Okay. So so you have x of k plus 1 is EAT. Sorry, x of k plus 1 is EAT x of k. So you can put this is basically k by definition, plus now you have this, okay, 0 t a alpha d alpha b, okay, and u of k. Okay, again the kt is by definition just a k, right? So you have this is AD and this is BD. Okay, this is exact discretization of x of t. Remember, we had this. Okay, after the Euler's first order approximation. Now this one becomes this, right? X of k plus 1, AD, xk, BD, uk. Now after this more proper approximation, now this x of t becomes x of k plus 1. Well, in fact, we start with this. Okay, so this one becomes now x of k plus 1 equals AD times 8a of k, and BD, so BD times u of k. Okay, so you see, like Euler approximation, and this is more or less like exact approximation. So this A matrix becomes what? A matrix becomes I plus AT, whereas this one becomes matrix exponential, so EAT. Still has a time, the sample time here, but it was I plus AT, but this one is E to the AT. How about the BD? It was the BT, and here you have 0t alpha t alpha times b. Okay. If you compare these two, now you can see that this one is kind of approximation of EAT. You know, by definition, EAT is I plus AT plus AT square divided by 2 factorial, etc. And only the first two terms are taken, okay, for this Euler's approximation. Right, so this is what I have written here, and you still have the same output equation. You can do this discretization using MATLAB, C2D, that's the command. So this G, that's the continuous plant. You can use SS command to define a continuous plant, okay, G, and C, continuous to discrete. So this is the MATLAB command, and using this command you can get a discrete model. And there are many ways of doing this discretization, as I mentioned before. And so if you just do this with no second argument, this one will use this exact approximation, but you could use zero order hold option, right? So here is zero order hold. So if you use this option, then the GD becomes I plus AT and BT, C, etc. Okay, so there are many options you can choose, but by default, the MATLAB will use this exact or proper approximation. How about the stability of AD? So last time we clearly saw that the stability of AD after Euler's first order approximation heavily depends on the sample time t. But this time we have to look at eigenvalue of e to the at, right? So, but eigenvalue of e to the at is eigenvalue of e lambda t, and the eigenvalue of this guy is basically this. So this is just a normal exponential function with the power of lambda 1t, lambda 2t, lambda 3t, lambda nt, and so on. So here the lambda 1 to lambda n come from the eigenvalues of original matrix. We know this guy is negative. The real part of these eigenvalues are all negative. And so um, as long as all the eigenvalues are negative, uh, in other words, all the eigenvalues are in LHP, then all these numbers here with whatever sample time t will be still in this unit circle. Basically, what you need in discrete the space is to have this circle. I mean, have all the eigenvalues inside this circle. This is real, imaginary, and we know the size of lambda should be less than 1. The size of lambda is defined by the circle, and we need this unicircle for stability because of this 1. Okay, so if all the eigenvalues are inside this the unicircle, then we can say this discrete system is stable. Okay, so if the say lambda, this lambda is negative number like minus 2t, right? Then we know this guy becomes 1 as t goes to infinity. If t is infinity, sorry, if t goes to infinity, it becomes 0. If t becomes 0, it becomes 1, right? But t is not equal to 0. So for whatever non-zero t, this guy, the size of this one will be always less than 1. Okay? For non-zero t. Okay? So any non-zero t will do the job, okay, for the stability. Okay, now we are going to see so-called realization technique. We have seen the conversion of state space to transfer function. The formula is given this way. But now we are going the other way. So the conversion of transfer function to state space model. Note that this formula is just unique, so that you are going to have a unique transfer function. So for given ABC, there is only one way, a single way to get to the transfer function. But this way is different. For this one transfer function, there are so many ways of doing these realizations that you are going to see. And the reason why we are looking at this realization is that, as I mentioned before in class, we often have transfer function in practice through experimental methods. So normally you can get poles and zero locations through exciting the given system. Okay, so once you have pole and zero locations, you can somehow estimate the transfer function, and then we need this conversion for state space, the control that we are going to learn. So to get the state model, we need the realizations from transfer functions, and there are several canonical realizations which are quite popular in practice. So here, this one, the first one is called the control canonical form, and second one, observer canonical form, and third one, Jordan canonical form. Here C stands for control, O for observer, and J for Jordan. And now here they all have a different state vector. So depending on the choice of state vector, here xc, xo, or xj, um, we have a different set of A, B, C. Okay, so we are going to see how we get these different canonical realizations by choosing a different state vector. But before looking at the realizations, we first look at the relationship between the state models first. Because I mean, they are all just different representation of the same system. And so here is xc, xo, xj, and even transfer functions must have certain relationship between each other. Okay. So here is one simple example. We have a mass spring damper system, and now for this the mass m, now we have acceleration my double dot, and this by dot ky like a reaction forces, and they actually came here with negative sign, but we take these two terms to left hand side, and we have this positive. Okay, so now suppose we are given this second order transfer functions, and then the first you can have a state vector of y and y dot. Okay, so these are just a typical choice. Okay, and then you can have a certain state model like A, B, and C. Right, this A is like a 0, 0, 0, 1 minus K minus B. I hope you remember this. Um, so given this, right, x1 dot is x2, and x2 dot is what this is y double dot. And so if you just divide the whole equation by m and take this two term to the right hand side, then you have b m y dot, which is x2 k over m x1 plus u. So from there we have x dot equals 0, 1, and minus k over m minus b of m, and x plus 0, 1 u. I have A matrix and B matrix. Okay. Of course, you can have output matrix as well. The CX, where C can be 1, 0 if the measurement is the displacement. Okay, so this is one choice. But suppose you have a different choice of state vector. Okay, for example, you want to define the first state variable as spring force. Okay, it becomes force. I mean, this is not the popular choice of state vector in this situation. But suppose this force, spring force, and damping forces are given as a state variable. Okay, for some reason you want to measure this force, and so this can happen. Okay, well, the Fs is at k times x1, right? Is spring force proportional to the displacement, the damping force, which is proportional to the velocity. Okay, so the first state variable is defined as k times x1 and z2 is v times x2. So now you can see there is some relationship between these two different choices of state vector, right? You can put this guy in matrix like this. Z is okay, so this matrix times x. Okay, so k1 times x1 gives you z1, and 1 of b times x2 gives you z2. Okay, so we are going to call this guy the matrix that relate these two state vectors is now called P matrix. Then the Z is equal to P times X, and is normally is invertible. Is one-to-one relationship. So if you know X, then you're supposed to know Z, and vice versa. Okay. Well, by choosing the state vector, we can also look at the state model. Okay, the state model is Z1 dot and Z2 dot, and right is k times what? K times x1 dot, and this is b times x2 dot. Right. In here, see this x1 dot is k times y dot, right? Because this is y and this is y dot, and so this is k times y and this is b times y double dot. Okay, but y dot is what is kbf b over b, right? This y dot, you see, fb, the damping force. Okay, is it b or the, yes, b. Fb is b times y dot, right? So, and this is we call this z2, and so y dot is z2 over b, and you just plug in here. Okay, then you have this, right? So is k over b times x2. Here x1 is z1 and this is z2. Okay. Okay, let me use just different notations to clarify the things. And so now in a similar way, the z2 dot will be b times, and y double dot is basically u minus by dot minus ky, and divided by m, and so we have this. Okay, so in the end, z1 dot will be k over b z2, and z2 dot will be times minus 1 over m fb, and z2 1 over m z1, like this. So my point is, you are going to get just different state model, right? Your A matrix will be 0 k over b. Your B matrix will be minus b over m, and your minus b over m, right? So this is your A matrix, and you are going to have the different state model in the end. Okay, so then so what is the relationship between this original state model? It's not original one, but just one state model corresponding to this choice of state vector, and you're going to get so different one, like a bar. Let me use bar to denote just different state model. So z and b bar, u and y, c bar, z. Okay, so this is different state model. And we saw that X and Z are related to this P matrix. And so this ABC here must be related to this A bar, B bar, C bar through something like P. Okay? And we all know that this state model should give us G of S through this formula. And also this one, this guy must give us the same transfer function through this formula as well. Because these are just a different representation of just one system. This one system. Okay. So to get the relationship between these two, you can just simply plug in a Z here. Okay. So Z is P times X, and so you plug in these expressions here and here, and then what happens is Z dot will be Px dot. You just differentiate this. P is constant, X is variable, and X dot, and A bar and Z and P times X plus B bar U. Okay, and here comes Z, and so Y is C bar and P times X. Okay, because P is invertible. Okay, you just pre-multiply the whole equation by P inverse. Then now these two cancel, and X dot P inverse A bar P X. Okay, this one times this, and P inverse B bar U, and Y equals C bar the P X. Okay, and now I want to compare this one with this. Okay, the left hand side is X dot or Y, and so this right hand side expressions should be the same. Okay, so if we compare this A part, then is P inverse A bar P is A. This one here, P inverse B is B bar, sorry. And here, the C bar P equals C. Okay. Okay, then what you can say is now A bar is P A P inverse. Okay, just simply pre-multiply with P and post multiply with P inverse. Then you've got this. Okay, and B bar here. So B bar should be P times B, and C bar should be C P inverse. Okay, just post multiply with P inverse, pre-multiply with P. Okay, so here A bar is PA P inverse, and the B bar is PB, and C bar is C times P inverse. Okay, so and so this tells us how to get the relationship between two different realizations. Okay, we have one realizations based on Z and the ABC. So this is another realization based on this X. Okay, but if you know the relationship between Z and X, okay, through P, then you can use this P to relate these two realizations.